Ladies and gentlemen, welcome to our today's class. And this class is on electrical circuit analysis in Diploma Module 2. And the topic of discussion is network theorems. Now, there are several network theorems to be discussed, but for today, I only want us to focus on Thevenin's theorem. The example that I have on the board is on Thevenin's theorem, and it reads, for the network shown below, determine the current through AB using Thevenin's theorem. And if you look at terminal AB, it is connected across the 10 ohms plus J16 ohms. So this load here, the 10 plus J16, will actually act as our load. So according to Thevenin's theorem, there are several steps that must be followed. Step 1, we need to get the Thevenin's voltage. And the Thevenin's voltage, that will be the voltage across terminal AB when the load is removed. That will give us the Thevenin's voltage. In the next step, that is step 2, we need to get the Thevenin's impedance, which is actually the internal impedance of the circuit, looking back into the circuit from terminal AB, with all sources of EMF replaced by their internal resistances. So that will give us the Thevenin's impedance. Then in our step 3, we need to come up with the Thevenin's equivalent circuit. Thevenin's equivalent circuit. Then from the Thevenin's equivalent circuit, we'll be able to clearly calculate the current across the load. And in Thevenin's equivalent circuit, the load is now brought back into the circuit. It is a circuit that comprises of 3 parameters. That is the Thevenin's impedance, the Thevenin's voltage, and also the load. That is impedance across terminal AB. So in my first case, that is in our solution, I want to now get the Thevenin's voltage. Now, if you look at the circuit, I've just said that the Thevenin's voltage is the voltage across terminal AB when the load is removed. So our circuit will now look like, okay, we need to find Thevenin's voltage, V Thevenin's. And the circuit that will lead us to get that is as shown. We have 30 at an angle of 30 volts, 30 at an angle of 30 degrees volts. We have 10 ohms. We have negative J, 15 ohms. We have 2 ohms. We have J, 3 ohms. We also have 10 ohms in parallel. And terminal AB. So according to Thevenin's theorem, we remove the load. And after removing the load, we need now to get the voltage across terminal AB. And if you look at the circuit keenly, you'll realize that the voltage across terminal AB is actually the voltage across the 10 ohms. Is the voltage across the 10 ohms. AB is in parallel with 10 ohms. So we need to get the voltage across terminal, or we need to get the voltage across 10 ohms. And studying the circuit, look at the supply. The supply is on this far end. Therefore, for us to get the voltage across the 10 ohms, we need to calculate the current that will be flowing through the 10 ohms. The 10 ohms. And we'll now start by getting the Thevenin, or the total impedance, total circuit impedance. Total circuit impedance. The total circuit impedance is given by the 10 ohms plus, now being that AB is an open circuit, so the current that is supplied will pass through 10, then reaching the junction, after reaching the junction, it will split into 2. So that from there, we'll now get the current flowing through the 2 ohms, J 3 ohms, and the same current will go through the 10 ohms because the 3 components are in series. Therefore, now I have 10 ohms plus negative J15 in parallel with the 3 in series. That is 2 plus 10 because of the real parts. 2 plus 10 will give me 12 ohms or 12 ohms. That is now 12 plus J3. So the negative 15, the negative J15 ohms is in parallel with the 12 plus J3 ohms. So this will give me the circuit impedance. And that is now equals to 10 plus, this is a parallel circuit of 2 impedances. That is product over sum. So I'll be having negative J15 into 12 plus J15, J3 all over sum, negative J15 plus 12 plus J3 plus J3. Now this will give us circuit impedance as 10 plus solving the parallel part will actually lead us to 10.93 at an angle of negative 30.96 degrees. So converting this one into rectangular form will give us 10 plus 9.37 minus J 5.62. So that gives the circuit impedance as 19.37. That is this plus this, the real parts, minus J 5.62, which we can as well convert into polar form. And when we convert it into polar form, we get 20.17 at an angle of negative 16.18 degrees. So from there, we can now get the current that is supplied. We can get the current that is supplied by the 30 at an angle of 30 volt or 30 degrees volts. So the current supplied, that is I, will be equivalent to V over Z total. And that is equals to 30 at an angle of 30 degrees volts divided by 20.17 at an angle of negative 16.18 degrees. So when that is solved, we'll actually get the current supplied as 1.49. That is obtained by dividing 30 by 20.17 to give us this at an angle of 30 minus negative 16.18, and that will give us 46.18 degrees. So this is the current that is supplied by the source. Now, looking at the nature of the circuit, you will realize that the current that is supplied from the source, after reaching this junction, it will divide into 2. And using the current divider rule, you will find that the current flowing through this branch, that is the branch of 2, 3, and 10 ohms, will be equivalent to the opposite impedance all over the sum times the current entering the junction. And that will be equals to, let me call this one I1 and this one I2. So the I1 will be equals to the opposite impedance, which is negative J15 all over the sum. The sum, that is negative J15 plus 2 plus J3 plus 10 times the current entering the junction. And the current entering the junction is 1.49 at an angle of 46.18 degrees. So when this one is solved, you can see 15 converted into polar will give us 15 at an angle of negative 90. That is negative J15 converted into polar will give us this. All over, this one here is 12 minus J12 times 1.49 at an angle of 46.18. So when this current is solved, it actually gives us the current across the 10 ohms, because you can see that the 10 ohms is in series with 2 plus J3. 2 plus J3. So that gives me 1.32 at an angle of 1.18 degrees amperes. That is I1. So the Thevenin's voltage, the voltage across terminal AB, VAB, is actually equals to the Thevenin's voltage, which will be equals to the current, which will be the current times, the impedance, which is actually the 10 ohm resistance. So I will be having now 10 times 1.32 at an angle of 1.18 degrees. Now the 10 being a resistive, or 10 ohms being resistive, it is actually at an angle of 0 degrees when converted into polar. So what we expect to get at that point is now 10 at an angle of 0. And when this is multiplied, it will actually give us a Thevenin's voltage as 13.2 at an angle of 1.18 degrees volts. So that is Thevenin's voltage. Now, after obtaining the Thevenin's voltage, which is actually the voltage across terminal AB, we need now to move to the next step. And the next step is to obtain the Thevenin's impedance. And in Thevenin's impedance, as I said earlier, it is the internal impedance. It's the internal impedance of the circuit, looking back into the circuit from the terminal AB. So in that case, our circuit will, the circuit that will help us to obtain the Thevenin's impedance will be as shown. It will be as shown. As I said that the load is removed. The load is removed, and the source of EMF is replaced by internal resistance, if any. But in this case, there is no internal resistance for this supply, and therefore I will just replace it with a short circuit. So we now need to get the Thevenin's impedance. Thevenin's impedance. That is Z Thevenin's. So the Z Thevenin's is the internal impedance of the circuit looking back into the circuit from the terminal A, terminal AB. So if you look at the nature of the circuit now, we assume that the supply is on terminal AB, and the current that will be supplied is in that direction. And therefore, looking at it from the supply end, it means that the two impedances here are in series and are in parallel. 10 ohms is in parallel with negative J15 ohms. And the combination here is in series with the 2 plus J3. Then the combination of the two is in parallel with the 10 ohms. so that our Thevenin's impedance, Z Thevenin's, will be equals to 10 ohms in parallel with 2 plus J3 in series with the 2 in parallel. 10 in parallel with negative J15. 10 in parallel with negative J15. So we can talk of for the inner parallel circuit. For 10 ohms in parallel with negative J15, we get product over sum. That is 10 times negative J15 divided by the sum, which is 10 minus J15. And this gives us, this is solved, that is solved to give us 8.32 at an angle of negative 33.69 degrees, which we can as well convert into rectangular form. And when you convert it to rectangular form, we'll get 6.92 minus J 4.62 ohms. This one is just the 10 ohms in parallel with negative 15 ohms. Now, if you look at this, you can see that the Thevenin's impedance will now be equals to 10 in parallel with 2 plus J3 plus whatever has been calculated here. That is the 10 ohms in parallel with negative 15 ohms. And that is now 6.92 minus J 4.62. So from there, you can see that J or 2 plus J3 is in series with 6.92 minus J 6 or 4.62. So that the result on the right hand side will give us 2 plus this, that is 8.92 minus J 0. minus J 0. That is 4.62 minus 3. J 1.62. And you can see it is negative. So now moving to the next page, let's continue on the next page. On the next page, so continuing on the next page, you can see that the Thevenin's impedance is equals to 10 in parallel with 8.92, and because of two impedances in parallel, we simply talk of product over sum. That is 10 ohms times 8.92 minus J 1.62 all over the sum, and the sum will be 10 plus 8.92 minus J 1.62. So this will give me 89.2 minus J 16.2 all over 18.92 minus J 1.62. So the result that will be obtained from here, which you can as well convert into polar form for easy division, or you can as well divide them in rectangular form. But the result that will be obtained here is equals to 4.77 at an angle of negative 5.4 degrees. That is in polar form, or in rectangular form we have 4.9 or 4.75 minus J 0.45 ohms. So that is the Thevenin's impedance. Now, after getting the Thevenin's impedance, as I mentioned earlier, we need to come up with Thevenin's equivalent circuit. And Thevenin's equivalent circuit, that is simply the Thevenin's voltage, V Thevenin's, which is, in our case, we had calculated the Thevenin's voltage. We had calculated the Thevenin's voltage, and we found it to be 13.2 at an angle of 1.18 degrees volts, supplying a series circuit of Thevenin's impedance, Z Thevenin's, which we have also calculated up here, and that is 4.75 minus J 0.45. So this is actually in series with the terminal AB. And remember, there was a load connected across terminal AB. And that load was the 10 ohms in series with J 6 ohms. So we need to bring back the load, and then we get the current across terminal AB. And the current across terminal AB will be in that direction. We can call it the load current. So if you look at the nature of the circuit now, the Thevenin's impedance is supplying the two impedances, the Z Thevenin's and the load. So now, this will give me the load, that is ZL. The two combined will give me the load impedance. So the current across the load will now be equals to the Thevenin's voltage all over the Thevenin's impedance plus the impedance across the load. So we have the two impedances. That is Thevenin's impedance and the impedance of the load in series. That's why we add. So therefore now, the current across the load will be equals to Thevenin's voltage, which is actually 13.2 at an angle of 1.18 degrees, divide by Thevenin's impedance, which is 4.75 minus J 0.45 plus 10 plus J6, that is for the load. So this is actually solved to give 13.2 at an angle of 1.18 degrees. We divide by 4.75 plus 10. That will give me 14.75. 14.75 plus J6 minus this will give me 5.5. 5.55. So from there, now we can divide this to get the current across the load. And when you divide that, you actually get 0.838 at an angle of negative 19.44 degrees amperes. So this will give me the current across the load. So you can say therefore, current across AB, that is IL, is equals to 0.838 at an angle of negative 19.44 degrees amperes. So we have actually calculated the current across the load, that is terminal AB, using Thevenin's theorem. So basically, if you look at what we have just gone through here, it is actually a three-step process whereby we get the Thevenin's voltage, that is the voltage across terminal AB when the load is removed. Then in the next step, we obtain the Thevenin's impedance, which is the internal impedance of the circuit, looking back into the circuit from the terminal ABN. And in step 3, we obtained the Thevenin's equivalent circuit. The Thevenin's equivalent circuit, which we actually have here. So this is what we, of course, call the Thevenin's equivalent circuit. So from the Thevenin's equivalent circuit, we ended up getting the current across the load, which is actually 0.838 at an angle of negative 19.44 degrees amperes. So you can see that that current is lagging. It is lagging by an angle of 19.44 degrees. So that marks the end of our today's example on Thevenin's theorem. And in our next lesson, we'll look at now examples on Norton's theorem. And thank you for now. May God bless.